Hello, today we talking about the lab is so-called consolidation test. So what is the consolidation? The consolidation test we can define that the other name is so-called one-dimensional compression. The meaning of the one-dimensional compression is that we have a soil specimen and we put the soil specimen in the ring. The ring here is confined the soil, so that means the soil cannot have lateral strain. Lateral strain equal to 0, that means it's constrained. After that, we apply the loading on the soil. So that means the soil will compress in only one direction. It means they have only so-called vertical deformation. Is only the vertical. They have no lateral deformation for the soil. And at top, above the soil specimens, we put the so-called porous stone at top and bottom to let the water is drained from the soil to the top direction and to the downward direction. This one is the concept. And if we do something like that, what's going on? The objective for test for consolidation test, we would like to monitor two objectives. The first one is the settlement, and the other one is so-called rate of settlement. So this one we try to explain the behavior of this test by the so-called Kelvin model. The Kelvin model is something like this. Firstly we try to compress the soil in this direction, and the soil itself or a structure of the soil is represented by so-called spring. Okay, at the starting point, when I apply the load to the soil and I close this valve, the stress will transfer directly to the water. Okay, that means if we apply the load about 200 Newton, firstly the water is carry the load about 200 Newton. After the valve is open, the water is trying to flow out at this way. It's trying to flow out. When the water is trying to flow out, that means you can see from this, the load carried by water will reduce from 200 to 150. And the load will share to the carried by the spring about 50%. And after that, when the time is passed, the water will flow out from the soil. The load carried by the water will reduce from 150 to 100%, and the load carried by spring will increase to about 100. And they let the soil for a while. That means the load carrying by the water will reduce from 50. So that means load carrying by spring is become 150, and finally the load carrying by the water become 0. Load carrying by spring is become 200. The load carried by water, we can call this one is the pore water pressure. And load carrying by spring is represented by the effective stress. And the last feature of this one is the so-called degree of consolidation. Degree of consolidation is something like this. For this case, the load carried by spring about 50 and the load carried by the water about 150. So that means degree of consolidation is become 25. And For the last one, you can see that the degree of consolidation will increase from 25 to 50 to 75 and finally to 100. So you can see from this one the value that we would like to know from this test. The first one is the how much of the settlement. Okay, how much of the settlement? The settlement is at the final stage or the settlement at maybe any time. Maybe this one is the settlement at any time. So that means according from this, the objective of the test, we would like to know first one is the settlement and second one is the rate of settlement. The machine that we use for test for consolidation test is something like this that we test in our lab. We put the specimen at this location and after that we add the load to the specimen. The load, if we take the moment at this point, is so-called point O. Okay, we can calculate the force that acting on the specimen is depend on the beam ratio. Beam ratio is the B over A. For example, if we adding the load at this point is equal to 100 kilonewton. The load acting at this point, P here is equal to 100 multiplied with B over A. So that means in your machine, in your lab, you have to know how much of the beam ratio and use this value to multiply with the load acting at the location the load applied. And the beam ratio, actually this one can vary from this one 9 to 1, 10 to 1, 11 to 1 is the beam ratios. And it's not only the beam ratio here, you have to monitor the deformation by using the vertical dial gauge that you put this one. When you record the settlement from dial gauge, the result is something like that. The x-axis is the time that you monitor. In our lab, we will monitor about 24 hours. And the y-axis is the compression or is the settlement of the soil. So if we get this kind of curve, we can know how much the settlement. This one is the settlement, and we know the rate of settlement. That means at this point, maybe if you test about 24 hours, this one is about 6 hours, you can calculate how much of the compression at 6 hours. Or this one is about 12 hours, how much of the settlement at 12 hours. So we have to determine the parameter for consolidation from this curve. We will talk about how can you get it later. If we apply the load to the soil, the behavior of soil is same as the behavior of the other enduring material. This one is the elastic plus is the stress strain curve of the steel. When we apply the stress, load will increase something like this to this point. This one is so-called elastic limit. If the stress is not beyond the elastic limit, it will come back at the same line. So this one is in elastic. If the stress is more than elastic limit, it become in here is so-called plastic. And after that, when we unload, the loading will come back to it here. It's composed of two components. The first one is plastic strain. It's the component that cannot recover from the deformation, and the other one is called elastic strain, is the one that it can be recovered. This one is the typical behavior of the material. Soil, steel, concrete is the same. For the soil, actually we plot as the same as this curve. We plot the y-axis is the we change from the strain to be void ratio, and the y-axis is the stress, and we using the log scale. Log scale we use log scale because we would like to enlarge this scale. And we plot, we apply the load to the soil. Compression curve is something like this. It's similar to, you can see, and this to the concrete, and this one is the yield stress of the soil. When you unload, if the stress is not more than yield stress, the load will come back at the same line. This one is elastic. When you adding the load more than the yield, the stress will increase up to point C, and if we unload it back, here it's become elastic. Okay, so that means the typical stress strain curve and the stress strain curve for soil is the same. Instead of we using the strain to plot in the x-axis, we change from the strain to be, here is void ratio. This one is a curve that you have to plot to send it to me. But for the soil, we not plot in this way, we rotate. We rotate the curve. The curve will be something like this. The y-axis is void ratio, x-axis is log stress. And we adding the load from this, and we had to move it back. When we add the load, we have to add the load in load step 1, 2, 3, 4, for example 5, 6, 7, 8, and so on. Okay, each load, when you apply the load, you have to wait. You have to wait. You have to wait. How long you wait? According to ACM, each load you have to wait about 24 hours. We have to wait about 24 hours for each loading. We have to wait. That means in this test, if I using the loading steps about 24 hours, that means you have to test it maybe more than 1 week. If you test it more than 1 week, that means it's the good news for you. For the next week, you have no need to submit the report. You can submit to the next 2 weeks. Correct? So that means you have a lot of free time for next week. You just monitor the load for testing. This one is the one curve that you have to submit it to me. This curve, actually, we can interpret from this curve. We have the slope from this to that. This one is so-called CR, compression index. And from this to that, this one is called CC, is so-called compression index. And after that, the load will recover up to this point. This one is so-called swelling index. So that means you have to report to me the first one, how much for compression index, recompression index, how much for compression index, and the last one is how much for swelling index. It's not only this, you have to report the yield point of the curve. But for the actual test, the curve is not linear like this, it's non-linear. So how can you determine the yield point? You have to do something like this. It's the graphical method to determine the yield point. The first one, you have to specify maximum point of curvature here. Maximum point of curvature. After that, you draw the horizontal line like this. And after that, you draw this line. It's a tangent curve to the maximum curvature. It's line number 2. And after that, you draw line number 3 up to here. Okay, sorry, you draw the line number 3. Line number 3 is the bisector. Okay, it's you have to divide the angle between line number 1 and line number 2, the same bisector. After that, you draw the last one is line number 4. This cross section is so-called maximum path pressure, or is so-called elastic limit of the curve. Okay, we go back to this one. Firstly, draw line number 1, draw line number 2, draw line number 3 is the bisector, and draw line number 4 here is the pre-consideration pressure, or the U of your test. Okay, this one you can report to me is so-called pre-consolidation. Pre-consolidation pressure. And this one you can use the curve to determine the settlement. The other one, you have to determine the parameter that you use for to calculate for the rate of settlement. The rate of settlement, how can calculate? I think you study in soil mechanics, but the parameter you have to calculate is so-called CV. CV is coefficient of consolidation. Firstly, you plot the curve is so-called log time. Something like this. Each load you plot the log time. Log time is this one is the x-axis is the time in log scale, and the y-axis is the compression. The curve will be something like this. How can you working around with this one? Firstly, you select the point A. The point A is the time number 1. Okay, and you multiply the T1 with 4. It's become point B. For example, if T1 equal to 1 hour, you multiply with 4 to be 4 hours. After that, you just determine this. Sorry, you have to determine this distance, and you project it back to the 0. The distance CA and AD is the same, similar distance. You can get this one is so-called D naught. D naught represents the starting point of consolidation, or consolidation equal to 0%. And after that, you have to determine the point of 100% for consolidation. You just draw the line. It's the tangent line from F to D. And the other one you have to draw, the other line is the BA. The cross section between two lines, it can be determine the value of the 100% of degree of consolidation. So that means you get this one is 0 and 100. You divide by 2, you can get the 50% of consolidation. This one is 50. After 50%, you project it up. You can obtain the so-called T50. T50 is the time that consolidation finishes about 50%. How can you calculate? You just use T50, subtract in this equation, and TV here equal to 0.197. H is the gradient length. Gradient length of this one you can see from this specimen. Gradient length is the water can flow up and can be flow down. So the gradient length of this one is the T. H here is equal to T over 2. You can subtract this value to the H over 2. After that, you can calculate how much of the CV value. So this one is a CV for log time. If you cannot catch this one, you can replay for the grip, and you can see. I hope you can understand how can you obtain the value for the CV. The other one is the CV for root time. Instead of plot with the log time, you plot is the square root time. The x-axis is the root time, y-axis is the compression. Firstly, you draw this line. Okay, you draw this line, then you determine this distance PQ. This distance. After that, you determine the so-called PR. PR is from this to that. It's a PR. PR is equal to 1.15 PQ. Can get this line. After you get this line, you draw the straight line. Up to this point. This point is the time for 90% of consolidation is the T90. After that, you just subtract the T90 in this equation. Subtract the H is the thickness of the specimen divided by 2. T is equal to 0.848. After that, you can calculate how much of value of CV for root time. The final report of this lab is something like this. Firstly, you have to plot between void ratio and stress. You have to determine the CR, CC, and CS. And it's not only this, you have to determine the CV value for each loading. In this lab, we have two methods for determining the CV value. I let you to use only one method, so-called log time method. So this means in this lab, you have to plot the curve. This one is one curve, 2, 3, 4, 5, 6, 7, you have 8 graphs for this lab. So that means you have a lot of curve, and that you can use Excel to plot the curve. But for the graphic, you have to draw by your hand. So that means every student, the value of the graphical method, it should not be the same. It should be the same. That means you copy from your friend.